Okay, so besides classification, another important task studied in the supervised learning is called regression. Regression is different from the classification. Regression mainly focuses on predicting some real number values as output. It's not for the class label to be predicted. We want to get some values to be predicted. We can provide you with an example like stock price. Given the stock price until today, can we predict the stock price for tomorrow? We want to get a number, right? What we want to predict is a number. It's not a class label. It's not a class labels anymore, right? It's different from a dog versus cat, bird versus fish, right? What we are predicting here in the regression is some real numbers, like the stock price, right? So the regression task differs from classification in the domain of labels. Instead of inferring the predefined classes that the data instances belong to, regression task aims to predict some real number value attributes of data instances. We show you some examples here, like box office of the movies, right? Given the movie's general information, can we predict what kind of box office the movie will get? Or the stock price for the market, right? Or the population for a country in the next year, right? What we are predicting here, they are all the numbers. It's different from the class, right? And the inputs will be very similar as classification. Actually, we also have a training set because we also have to rely on the supervised information to train a model. We have a training set involving both features as well as y. This y denoting the real values, like the population or stock price or the box office of some movies, right? They are all the numbers. And we want to train a model, a regression model, which can predict these numbers out for us. In this page, we can show you with a very simple example with a linear regression model. The linear regression model is very similar to the subtle vector machine we showed before. However, we don't require it to predict the labels. The linear regression model also have the parameters, the W. And we also have this bias as W0, right? So in other words, we can incorporate all the parameters into one single vector, W. W0 denoting the bias term, W1 until WD denoting the weights for different features. And the model we are defining is a mapping. The function mapping we define here denoting the summation or the weighted summation of all the features of the data instances plus the bias term, right? Given a data instance with the features, we can generate its output as this according to this function, right? And it's W vector denoting the weight parameters of the regression model. And how can we learn this model? So for learning the model, we require some training set, right? Let's assume given a training set involving both features and knowing value outputs, we can use it as a training set. According to the linear regression model we defined before, we can generate some predicted values by the model, right? And we can further compare the output by the model versus the true outputs of the instances, right? By comparing their differences, we can define the difference or the loss term for model learning, right? Linear regression will use the sum of squares between the predicted labels versus the ground truth as a loss function. So formally, we can repeat the loss function as shown here as E, Y hat, and Y. Y hat covers the prediction of all the instances, and Y denoting vector cover all the true outputs of the labels of the instances in the training set. We can define the E function as the sums of squares between the true outputs versus the predicted outputs, right? So by summing them together, we want to minimize the loss function. So to train the model, right? You can follow me, right? So given the model, we can generate the predicted outputs by the model, and we can compare the predictions versus the true outputs. And by comparing them, we can define the loss function. We want to minimize the loss function, of course, right? So according to the equations we define here, we can define the loss function to be what? To be xw minus y. This X will cover all the feature vectors in the training data. Each one will be a vector. However, if we combine all these n different instance feature vectors together, we will define one matrix, right? X matrix. If we organize all the true values of the instances in the training set together into a vector, it will be a Y vector, right? And this W is the weight we defined before for the model. So by minimizing this term, we will be able to learn the optimal W for the model, for the linear regression model. So you may wonder, how can we solve this optimization problem? Later on, we will have one section on the optimization specifically for you. And here for this setting, we have a very special solution because we can get a closed form solution for this problem. To minimizing this term, we can do is to calculate the partial derivative of this term regarding this W, right? We can calculate the partial derivative of this loss function versus W. It will be equals to what? It will be equals to 2x transpose times xw minus y. So we can, by making this term equal to 0, we can get the closed solution of this W to be what? To be x transpose x, the inverse, times x transpose times y. Right? Because this one is a very special case. For this problem or for this model, this setting, we can get the solution, the closed form solution of the model to be shown here. Of course, here we have an assumption. To make this solution can hold, we need to ensure the inverse of this term can exist, right? In other words, we need to assume this x transpose x is invertible. And the loss function we're defining here is actually called a square arrow. And this arrows used in the linear regression model has very good properties in math. And it corresponds to the Euclidean distance actually. Meanwhile, the method of computing the minimum based on the square arrow is called least square method. You probably have heard about this before. And so this is a very special case. You see, in this linear regression model, we can predict the outputs of the data instances based on this linear model, right? And we can get a closed form solution via some properties of this loss function, right? And besides this linear regression model, we can also define some other regression models as well. Two other famous regression models also based on the linear regression model. They are the variants, right, of the linear regression model. The first one is called ridge. The ridge regression will address some problems with a conventional linear regression model by imposing a penalty on the size of coefficient. So the loss function will be the same. However, besides this term, we also add one more term on recognizing the weight or the W, right? So we can define the objective function to be minimizing of the loss function as well as the recognition term. So for this kind of case, because this recognition term is based on L2 norm, and we can also get an optimal solution for the ridge regression as well. And we can represent the optimal solution to be shown here. If you are interested in them, you can also derive them by yourself on your paper. It will be very straightforward. Okay, besides the ridge regression, another regression model which is also very used in the machine learning is called Nassau. Nassau is also a linear model which estimates the sparse coefficients. It is very useful in some contexts due to its tendency to prefer solutions with fewer parameter values. So the Nassau regression, the objective function is very similar to linear regression as well as ridge regression. The main difference is that it changes the loss function to be the mean square arrow. At the same time, the recognition term is based on L1 norm. Here we have L2 norm. For the linear regression, we have no norm at all, right? For this Nassau, because of this L1 norm, can ensure sparsity of the model in terms of parameters, so we can never spot parameter coefficients for the model. However, this L1 norm is not differentiable. It makes some problems for learning of the model. And we have no closed form solutions, but it can be addressed with some methods like subgradient methods, least angle regression, and some proximal gradient methods. They are all beyond the scope of this course, so we will not cover them here. Okay, so these are all the regression models we can study. Okay, we can use for the regression settings. You can see the difference of the regression versus classification, right? And you can also see the different regression models: the classic linear regression, the ridge regression, and the lasso regression models. So besides them, we also have some other regression models. You can maybe check them by yourself after class if you are interested in them. However, for this course, majority of the problems we are studying, they are all based on the classifications. But we will borrow some ideas from regressions for defining loss functions, for the organization terms, as we can see here. Okay, so this is about regression, and we can move to the last task on the class string for unsupervised learning next.